Guys, I hope everyone had a good weekend. Those of you in person, I just passed out your test 2 for you to look at. Those of you who took the test at home, it was distributed back out to you. Then those of you who took it in person, but you're home today, I'll just give you your tests when you're back. I'm not going to spend too much time going over the tests right now. They were overall pretty decent. Some common mistakes I kept seeing was obviously just like some simple stuff like some bad algebra happening. But also stuff like make sure when you have a graph, you justify your answer based off of the graph that was given. And then I'm still seeing also mistakes when it comes to how you justify using the second derivative test. But I did share the answer key with you. If you go into OneNote underneath the Unit 3 tab and then the Assessments tab, I did share the key with you so you can check the answer. This unit is Unit 4. This is the calendar for it, so we're doing more derivative applications. We're going to start off the unit just learning our last set of derivative rules that we need to learn. Remember, there are no formula sheets on the AP exam, so all these rules, of course, have to be memorized. Tuesday and Wednesday, we're going to be looking at related rates, which is our first type of calculus word problem that we have to be able to do. And then your quiz is actually on Friday, so like real quick for this week. And then the rest of the unit is kind of weird just because we have a lot of weird days here at Roswell. Not sure how well it's been communicated, but next week, Tuesday and Thursday are not normal school days. Monday, Wednesday, and Friday are regular days. When you're looking at Tuesday and Thursday, it's by whatever grade you're currently in. So on Tuesday, the 27th, the only people at school are going to be 9th graders and 12th graders who have previously signed up for the SAT with their counselor. Everyone else will be asynchronous that day. I don't plan on doing anything new that day because my classes have a mixture of mainly 11 and 12, so it doesn't really make sense for me to do too much. So it's just going to be like, hey, work on homework or whatever else you need to. Wednesday's a normal day, and then Thursday next week is the PSAT day. For 11th and 12th graders, 10th and 11th graders. It will be asynchronous for 9th and 12th graders. Both of those weird days are also going to be early release days. So whether you come to school on Tuesday or Thursday next week, the school day is ending at 12:40. So a little bit weird next week, and then the week after also you have Tuesday off for election day. And so then pretty much after the quiz, we're going to be learning about absolute extrema versus the relative extrema, optimization, which is the second type of calculus word problem we have to know, and then we're actually ending the units with kind of how we started the school year with limits by learning about L'Hopital's rule. And then your test is going to be that first week in November. So today we really are just going to be looking at some derivative rules, and we're going to be learning about the inverse trig derivatives. Again, these are just rules you have to memorize, but all that stuff we did in Unit 2 and Unit 3 is not going to go away. Still have to do like interval increasing, still have to do concavity, still have to do extrema, points of inflection, tangent lines. Anything we've learned can definitely show up, especially when we're just learning some new rules. So I did want to review a little bit just about inverse trig functions and things like that. So just to remind you on inverses, in mathematics, inverses we know are kind of like the reverse of a function. And in math, we often define an inverse to make it a function. So basically that it will pass the vertical line test. So in math, I want to compare like two different equations. This first equation, I want to compare x squared equals 9 versus just saying x is equal to the square root of 9. And then I also want to be able to compare the equation, the cosine of x is equal to 1/2 versus x is equal to the arc cosine of 1/2. Looking at these, like in the square root one, if I have x squared is equal to 9, we know that we can go ahead and take the square root of both sides. And when I take the square root of both sides, I get x is equal to plus or minus 3. It has two answers because it's coming from x squared is equal to 9. I want you to compare that to if I just say, hey, what is x is equal to the square root of 9? We're not taking the square root on both sides. We're not really solving the equation. So when we see something like this, in math, this is called the principal square root or just the principal root, and it would just have one solution. The reason why it just has one solution kind of goes back to the idea behind just like functions in general. So we know for inverse functions, we could rotate the graph. So like y equals x squared looks something like this. But its inverse, if you just were to flip it normally, it would have these pieces both on it. But since that inverse is not a function, the domain and range is restricted, and the square root of x just includes the top part of the graph. So we only have one answer there. So if you remember from pre-calculus last year when we were doing trig, there's a difference between saying, hey, when is cosine of x equal to 1/2, and when is x equal to the arc cosine of 1/2. If we just say cosine of x is equal to 1/2, there's lots of answers there. So from 0 to 2 pi, x would be, when is cosine equal to 1/2? Cosine is equal to 1/2 at pi over 3 and 5 pi over 3. But we know if there's no restrictions, that that's going to repeat every period that you have. So it's going to start at pi over 3 and repeat every 2 pi, or it can start at 5 pi over 3 and repeat every 2 pi. So we have multiple answers there. Meanwhile, if I just say arc cosine, remember arc cosine is the same thing as saying the inverse cosine. That will only give you one answer because mathematicians have defined this as an inverse function. So it will only have one answer, one x for every y. And if I just say x is equal to arc cosine of 1/2, x is just equal to pi over 3 because we have restricted the domain. I go over that just because we often find ourselves, even though we're still doing like calculus with these functions, we still want to be able to like evaluate them and review what we know about them and what we learned about them last year. So when I say arc cosine has its domain restricted, I did want to kind of review that for the 3 that we covered last year. So last year we talked about arc sine, arc cosine, and arc tangent. And remember when I say arc sine, that's the same thing as saying the inverse sine. Arc cosine is the inverse cosine, and arc tangent is inverse tangent. College Board on the AP exams tends to use the arc versions more often, but they will use both of them. Just know that those are exactly the same thing. Arc sine, does anyone remember which quadrant arc sine exists in? First and fourth. So arc sine, remember it has to have different y values. The y values will be different in the first and the fourth quadrant. We can also think of it as its output is going to be between negative pi over 2 and pi over 2. Arc cosine is going to exist between which two quadrants? That one's in 1 and 2. The x value of cosine is going to be different between 1 and 2. And then tangent is going to be in which two quadrants? First and fourth. Technically, tangent does not exist at the reference angles of 90, but it's basically the same interval as arc sine. And so we remember that from last year, or if not, there you go. So if I ask you to evaluate an inverse trig, again, this isn't really calculus, but we know sometimes, say if I have to write like a tangent line, you need the y coordinate, so you do need to remind yourself how to evaluate these inverse trigs. They only have one answer because of those restrictions on the domain. So they're only going to be in 2 quadrants. The main thing to be careful with is in that fourth quadrant, you use like the negative version of the angle. So instead of saying 11 pi over 6, you would say just negative pi over 6. Or instead of 5 pi over 3, you would use negative pi over 3. So when is arc sine what is the arc sine of negative 1/2? The arc sine of negative 1/2 means the sine of some angle is equal to negative 1/2. And that would be negative pi over 6. If I say what's the arc cosine or the inverse cosine of root 3 over 2, that means when is cosine equal to the square root of 3 over 2? That is at pi over 3. And then arc tangent of negative root 3. That means when is tangent equal to negative root 3? We know we're in the fourth quadrant, and again, just to remind you, we know that tangent is the sine over the cosine. So that would be the format that would have given you negative root 3. So you're thinking about the coordinate that looks like this in the fourth quadrant is going to go with negative pi over 3. So that's just like a quick pre-calc review, way back from like unit 2 stuff of pre-calculus that we did kind of around this time last year. But now what we really want to focus on is the calculus. Did I mess up?
I thought cosine is pi.
Oh yeah, Mr. Brown's completely wrong. Definitely not that answer. Thanks. Root 3 over 2 is this one, pi over 6. Cool. 2 out of 3 for me. So then looking at the calculus of it, I could go through and prove for you kind of why the rule is the way it is. There are 6 rules that we have to know. So we have the rules for arc sine, arc cosine, arc tangent, but we also have arc cosecant, arc secant, and then arc cotangent. I'm not going to prove them all. Like I'm going to prove one of them to you, and the rest of them can kind of be proved in a similar manner. I also want to show you where it comes from, just to review some other concepts that we've done previously. So if I tell you to take the derivative of y is equal to the arc sine of x, like right now we don't have a rule on how to take the derivative of arc sine. But we can rewrite that equation to use rules that we already know. If I say y is equal to the arc sine of x, what's another way I could rewrite that equation without using the inverse trig?
Sine of x.
So we can reverse it, so it's going to be just regular sine. Sine of y is equal to x. So I can rewrite it. These two equations are equivalent, or I guess I should say like equivalent, like an asterisk by it. That first original equation has domain restrictions because arc sine has domain restrictions. Equal to the sine of y, I don't really have those restrictions on there. But by rewriting it, we can go ahead and use derivative rules that we know. What derivative process am I going to have to use to take the derivative of x is equal to the sine of y? Implicit. So we're taking the derivative of y with respect to x. So taking the derivative of x is just 1. The derivative of sine is cosine times dy dx. And again, I want to find what the derivative is, so I can just solve for dy dx. And dy dx is equal to 1 over the cosine of y. Now that's not really a very useful formula. Like no one's going to say, hey, what's the derivative of arc sine of x? And you say 1 over cosine of y. Like that's a true statement, but it's not the most usable derivative. So we kind of switch the variables around. But we can do some math to kind of rewrite it to look more algebraic. And where that comes from is we do have what we have the given information up here. So I know that x is the same thing as the sine of y. And then to also throw in some things from pre-calculus, I know that sine squared plus cosine squared is equal to 1. Now, where is this coming from? Like we know the Pythagorean identity. Where am I headed with this? Well, if I know that x is the same thing as the sine of y, I can go ahead and plug that in for the sine of y. And looking at the derivative we got, we saw that the derivative was 1 over the cosine of y. So in this expression, I can solve for the cosine of y. By solving for the cosine of y, that's going to become 1 minus x squared, and then we can take the square root of both sides. Technically, we know that when we do the square root, it's plus or minus. I'm just going to say, like, trust me on this, that's only the plus one. I could go into the math of it, but it's just basically because arc sine has restrictions on the graph. But basically, the cosine of y is equal to the square root of 1 minus x squared, which does kind of remind you of like a lot of stuff that we did in pre-calc, converting inverse trig expressions to algebraic expressions, and then also some trig identities. So the nicer way to write the derivative of the arc sine of x, instead of saying 1 over cosine, I can say 1 over the square root of 1 minus x squared. One interesting thing about the derivative of the inverse trig functions is like, so with regular trig, the derivative of a trig function is just going to be like another type of trig. The derivative of sine is cosine. The derivative of tangent is secant squared. Inverse trig is interesting because the derivative of an inverse trig function is actually going to be something that's an algebraic expression. There's going to be no more trig in the equation, and it is going to be basically like a type of rational expression. Now, you don't have to know how to prove that. Like, we could do this for all of them. I'm not, because just for the sake of time. I am, though, going to go ahead and just give you the 6 formulas you have to have memorized. But I think knowing where they come from can kind of help you when it comes to memorizing them. So we have 6 inverse trig derivatives you do have to know and memorize. Thankfully, there are a lot of patterns. Like, I really just memorized 3 of them because I know all the co-ones are going to be negative, and they're kind of like exactly identical except for a minus sign. So the one that we just did, the derivative of arc sine is 1 over the square root of 1 minus the inside squared. In these formulas, I put a u there instead of x just to remind you of like where the inside is. So if you have more than just x there, you're going to have to remember to use the chain rule. So I put a u there just to remind you, hey, sometimes you need to use the chain rule in these problems. In fact, typically you're going to have to use the chain rule in the problem. So the derivative of arc sine is 1 over the square root of 1 minus the inside squared, and that order does matter. For arc cosine, it's the same thing, but it's negative 1 over the 1 minus the inside squared, and then there's my chain rule. Arc tangent and arc cotangent, so it does come from a Pythagorean identity. If you remember this one from last year, since the 1 is on the same side of tangent, when we do rewrite the formula, if you were to go through the proof, there is no square root sign. I think it's easier just to remember inside squared plus 1, don't forget the chain rule, and then same thing for arc tangent, but it's negative times, there's my chain rule. And then the ones that are weird is going to be the derivative of arc secant and arc cosecant. So when you have the derivative of arc secant, there's like 2 parts to it. It's the product of secant times tangent. Well, the derivative of arc secant also has 2 parts, and it looks like this: 1 over the absolute value of the inside times the square root of the inside minus 1. There's my chain rule. Arc cosecant is negative in that same thing. Absolute value of the inside squared minus 1 times the chain rule. So those are the 6 rules that you want to have memorized. I don't have like the best tricks on how I kind of remember them myself. I was trying to think back to how I remembered them in high school, and like all I could come up with, I mean, I do remember for arc sine and arc cosine, those are usually the first trig ratios you learn, so they're the ones that have like the 1 coming first in the denominator. I don't know if you can think of something better. The arc tangent and arc cotangent have no square root on them, and it's plus. And then for arc secant, compare that to arc sine. So arc sine has 1 minus the inside squared, and arc secant has the inside squared minus 1. I just kind of remember that the insides have to be touching. So like they'll be next to each other, even though they're separated with like the square root sign and the absolute value. So today what we're going to look at is just practicing taking these derivatives. But more than that, like taking a derivative is fine, but we want to make sure that we can still use it to do different things. So like finding horizontal tangent lines, making sign charts, and things like that. Any question on those derivative rules? All right. So I have, let's find the x-coordinates at which the graph of y has a horizontal tangent line. So if I'm looking for a horizontal tangent line, we know that that basically is going to mean that the derivative is equal to 0. So go ahead and find the derivative of that expression for me. I think the hardest part of these problems is not, again, taking the derivative, but often like the algebra that comes afterwards with the simplifying and the solving. So in taking the derivative of this one, that 5 is a leading coefficient, so I'm going to go ahead and just bring that 5 down. Times, now I want to take the derivative of the arctangent. Well, arctangent is 1 over the inside squared plus 1, and then we don't want to forget about the chain rule. X over 2 is the inside. What's the derivative of the inside? What's the derivative of x over 2?
1/2.
1/2. So we can think of this as 1/2 times x, so its derivative is just 1/2. And then I have the rest of it, minus the derivative of 2x. The derivative of 2x is just 2. So the new part is, there's the derivative of arctangent. Here's the derivative of arctangent with the chain rule. So then the idea behind this, if we want to find where we have a horizontal tangent line, we need to solve this and set it equal to 0. That right now is not the friendliest equation to solve and set equal to 0. There's just like a lot of stuff going on. Then we have like this fraction over a fraction. So I definitely recommend simplifying it before you set it equal to 0 to make your life a little bit easier. When I simplify these, I kind of first like group coefficients together. So I have the 5 and the 1/2, which is going to give me 5/2 times, that's going to become x squared over 4 plus 1. I have this minus 2 hanging out to the side. To get rid of that fraction within a fraction, I can multiply it by 1, and the one I'm going to multiply it by is 4 over 4. In doing that, I want to make sure I distribute, but that is going to simplify the problem for me. So I end up with, there's my coefficient of 5/2. 1 times 4 is 4. Distributing that 4 across the denominator, x squared over 4 times 4 is just x squared. 1 times 4 is 4, and then we have the minus 2. 2 goes into 4 2 times. So a simplified, cleaner looking first derivative. 5 times 2 is 10 over x squared plus 4 plus 2. That derivative does look a lot easier to deal with. Like it's, if I was to choose that original one or that one set equal to 0, that one is a whole lot easier to set equal to 0. So go ahead and finish that problem out to find the horizontal tangent lines. Yes, ma'am. Where'd I get the what? It should be minus 2. Thanks. There. And you should get 2 horizontal tangent lines for this one. Different routes you can take to solve it. I went ahead and added 2 to both sides, and then I can think of that as 2 over 1. Fraction equal to a fraction, I can go ahead and cross multiply, and then making sure when we solve this, we take the square root. So we have 2 horizontal tangents at plus or minus 1. Any questions on that problem? All right, so part 2 of this problem, I'm just going to copy this, put it to the other side, is I'm going to take that same equation, and now I want
Wait,
to...
Mr. Brown, you didn't answer the question.
I think I did.
I thought it said the
The
line.
x-coordinates. Yeah, there we go, we're done.
Oh, okay. I thought you said the slope.
No, well, the slope would
actual
be
equation.
0, because it's a horizontal line. So go ahead and take that equation, and I want you to find whether that is a relative minimum, maximum, or neither. And so we saw the critical points was plus or minus 1. I would recommend to you, so where you need to make a sign chart is easiest when you have a single fraction. So I'd probably get a common denominator with that 2, so you can write it as a single fraction and then factor it. Because right now, that -2 is going to throw off your sign chart. I would get a common denominator and kind of go from there. And sorry if you thought you were done with sign charts after the last step. And so I know that I did that fairly quickly, but you do want to just be like pretty fluid and good with doing just like some quick algebra. So we already found the derivative, and again, for a sign chart, we know along that vertical goes our factors. Well, that 10 over x squared plus 4 and the -2, those aren't factors, those are separate terms. So by getting a common denominator, I can then simplify it and then factor it, and then I can easily make a sign chart. One nice thing is we could have simplified it first. So if I had simplified it first, it's almost even more obvious what the horizontal tangents are at, because we can see in the numerator that we clearly have horizontal tangents at -1 and +1 from that numerator. But looking at my sign chart, -2 is always negative. If I square something and add 4 to it, it's always positive. For x squared plus 1, anything you plug in that's less than -1 will be negative. Anything greater than -1 is going to be positive. For the next factor, anything less than -1 is negative. Anything greater than +1, excuse me, I said -1, +1 is going to be positive. So overall, we have a negative interval, and then a positive interval, and a negative interval. And from that sign chart, we can go ahead and classify our key points as minimums and maximums. So I have x equals -1, goes down then up. So it's a relative min because y prime changes from negative to positive. And then x equals +1 is a relative max because y prime changes from positive to negative. Again, you didn't have to do the first derivative test. I did, since I didn't feel like finding the second derivative, because that would have been just more algebra. But you could have found the second derivative and then done the second derivative test as well. Any questions on that problem? All right, I am going to give you some time and not rush you to try this one on your own first. So I want you to find the x coordinates at which y is equal to x times the square root of 1 minus x squared plus arc cosine of x has a horizontal tangent line. Again, similar to that previous one, I definitely recommend you simplify your derivative before you set it equal to 0. The last thing I'll say before I let you try it on your own, just make sure you follow all the derivative rules that we've learned. When I see this problem, I see an inverse trig rule, I see the product rule, and I see the chain rule. So have fun with that one. And to finish quicker before I go over it, the second part of this question is going to be classifying the horizontal tangent lines, minimums and maximums. So there's my unsimplified derivative. So I had the first times the derivative of the second. So 1/2 came down in front, new exponent's negative 1/2 times the derivative of the inside, which is negative 2x, plus the derivative of the first times the second, and then plus the derivative of our cosine, which is negative 1 over the square root of 1 minus x squared. So we want to find the horizontal tangent line. So you're going to set that equal to 0. And right now, that is not an equation I would want to solve by any means. But we can simplify it, and it does simplify pretty nicely. Most of the time, they're going to be written so that they do. So like if I'm simplifying this one, like this 1/2 is going to cancel out the 2. So I have y prime is equal to, I have an x times a negative x, so negative x squared. I'm going to send that term to the denominator, factor I should say, to the denominator. The second term looks like this, and then I have minus, and there's from the cosine. So if I'm looking at this, I do need to set this equal to 0, but right now I have 3 terms in here. So I would recommend getting a common denominator and then kind of adding them together. So I'm going to go ahead and multiply the second one by the square root of 1 minus x squared over 1 minus x squared, and then simplify it from there. So I have y prime is equal to, now they have the common denominator of 1 minus x squared. In the numerator, I have a negative x squared the square root of 1 minus x squared times the square root of 1 minus x squared is just 1 minus x squared, and then minus 1. The minus 1's cancel out, and I end up with negative 2x squared over the square root of 1 minus x squared. So this is my derivative, and then we do want to make sure we find the horizontal tangent lines. The horizontal tangent lines come when the first derivative is equal to 0, so that's going to be when the numerator is equal to 0, so we get x is equal to 0. One thing I just want to say as kind of an aside, especially after grading the AP exams this summer, is on a first response question, you always want to make sure that you're very clear where your answer is coming from. So like on the AP exam, it's kind of risky if you just had the derivative and then you jump straight to the answer if x is equal to 0. Like you would want to clearly say, hey, I'm setting the derivative equal to 0, or like this is what I'm setting equal to 0. But you do want to be clear about where that answer is coming from. I also recommend you do that because say if you just accidentally, like this one, you wouldn't solve incorrectly. But if you accidentally solve something incorrectly, you can earn partial credit by at least saying where your answer is coming from, which is nice. So looking at this one, we only have one horizontal tangent line, and that horizontal tangent line is at x is equal to 0. Go ahead and use that derivative and that horizontal tangent to classify that x coordinate as a relative min, maximum, or neither. So looking at this one, we have like two factors. You could say 3 if you wanted to split up the negative 2 from the x squared. Basically, that numerator is always negative, that denominator is always positive. So the derivative goes from negative to negative, so 0 is nothing. It's not a relative minimum or a relative maximum. This problem is actually one that we talk about a little bit later this unit. It does have absolute extrema on its endpoints. So this function, if you were to graph it, looks something like this. There's the x and the y axis. So it does have absolute extrema on the endpoints, but the relative extrema, there's not one at 0. Questions? 2 more problems. Try this one for me. Find the derivative of the function y is equal to the arc sine of x plus the arc cosine of x in simplest form. And then once you have that derivative, tell me what that means in the context of this problem. And so we have the derivative. Arc sine, arc cosine are basically the same derivative rules, but one's positive and one's negative. So what is the simplified version of the derivative for this function? 0. So basically y prime is equal to 0 like always. So what do we know about the graph of y is equal to arc sine plus arc cotangent of x? It's a horizontal line. So it looks fancy, but it's basically just a horizontal line. Maybe you think that's cool, maybe you don't. Specifically, the horizontal line y equals pi over 2, because the arc sine and arc cosine, the same value, will always add up to 90. And I have one more example. If you're following along in OneNote, I meant to add a page so it's not distributed, so I'm just going to kind of make it up. Did want to do an example with arc secant or arc cosecant, since they're not as common, but we definitely still need to know them. So go ahead for me and just find the derivatives of these two, and then we'll be done with today's notes. We'll do the arc secant of 4x. We will do the derivative of arc cosecant. Tried those two. So I have the arc secant of 4x and then the arc cosecant of x minus 2 squared.
Look at the hard thing.
It's just breadth. Separate it from so this first one, if you're taking the derivative of arc secant, so arc secant is the positive one. So you have the absolute value of the inside times the square root of the inside squared, and it's minus 1. Don't forget the chain rule. The derivative of that inside, the derivative of 4x is just 4. So you can just write this one as 4 over the absolute value of 4x on the square root of 16x squared minus 1. Do want to be careful when you're simplifying that one. Like, I think it's easier just to kind of leave it like that, because that absolute value, kind of traps certain things in it. But you can technically, since that coefficient of 4 is always positive, you can simplify it as 1 over the absolute value of x on the square root of 16x squared minus 1. But either of those last two answers would be fine. And then the second one, arc cosecant, has a very similar formula, but it's just negative. So I have negative 1 over the absolute value of the inside times the square root of the inside squared, so I have the whole inside squared, minus 1 times the derivative of the inside, so 2 is going to come down in front, x minus 2 to the first power, chain rule again, but the derivative of the inside is just 1. This one you can simplify it a little bit more as well, so you could just leave it like this as negative 2x minus 2 all over the absolute value of x minus 2 squared on the square root of x minus 2 to the fourth. And I would probably leave it like that just to be safest, but there are other ways you can simplify it. So if I had this x minus 2 squared, it's always positive anyways, so you can technically drop the absolute value there. And if you drop the absolute value, it does become this expression. And again, I could drop off that absolute value, except leave one of those there. Because it would be always positive. But the answer above it is also just fine to leave it as well. Any questions on those derivative rules? Go back to them. So those are the 6 rules that you need to know for inverse trig derivatives. Rules, like we have no more to learn. Don't forget any other ones that we have learned already, like the log ones or the exponent ones or the other trig. Your assignment for today, distribute in OneNote, but it's out of the textbook. Homework 1 is going to be inverse trig stuff. You're doing multiples of 4, 44 through 64, and then 70 and 79. You do not need to simplify any of them except for 2 of them, just because they're common problems, and I want you to practice the algebra. The only 2 I want you to simplify are 52 and 56. So you don't need to simplify all of them except for 52 and 56. Tomorrow we will start the word problems that we need to learn with related rates, and that's going to take me 2 days to do. Thursday is going to be a review day, and then your quiz, really just the 2 topics of inverse trig derivatives and related rates. So yeah, y'all can go ahead and get started on that. We have some time to get started, but definitely ask me any questions that you have, whether you're here in person or at home.